So let's then go to derivatives of multi-variable functions. So in particular, go to partial derivatives. So you remember that if you have a normal function of one variable, then the derivative of that function essentially measures how fast this function value f changes as you change the variable x. Now if you have two variables, of course, something similar will be the case, but now we have to agree that it's not so clear basically how fast what change basically means, because changes can occur in multiple directions. So if you think of somebody standing on a hillside, well, the hill might be sort of not so steep if you go one way, but if you go basically along a height line, you will not basically change your height. So you might say it's not so steep. But if you go directly to the top of the hill, it might be much cheaper. So it depends on what direction you're walking, how fast the height of the hill is actually changing. So indeed, the same thing happens here. So if you have these two variable functions here, so if it's f of x and y, we have to sort of identify the changes in the different directions that you might walk. So we see this actually in this particular graph. So the different rate of change when you walk in the x direction than when you walk in the y direction. But you have to identify both. So how would we do this formally? Well, actually, we just identify two derivatives. One derivative in the x direction and one derivative in the y direction. So how fast does z, the height, change as I move the x direction, and how fast does z change if I move in the y direction. So just from a definitional point of view, you remember perhaps that we defined these derivatives as limits of measuring essentially the slope of the tangent line to a certain graph. So here we have various tangent lines. So one in the x direction, and so that's essentially the first equation in this definition of a partial derivative. So if we look at the partial derivative, which is written with this funny rounded d, so a curly d it's called actually. So partial derivative of z in the x direction, that is the slope of the tangent line to this surface, right? It's a surface now. The slope of a tangent line which lies actually in the x direction. And similarly, the partial derivative of z with respect to y, it's curly brackets, and the y over here is what happens if I move in the y direction a bit, while keeping in this case actually x constant. So these are definitions. Let's have a brief look at notation. So I just introduced it. So if the function z equals a function of x and y, thus the height of this function z is a function of x and y, then equivalently we might write with these curly d's dz over d or dz over dx is the same as df dx, and sometimes we might write this actually as an f with an index x to make sure that it's going to be the partial derivative in the x direction and not in the y direction. And sometimes even we might write, instead of the index, we write the index number. So it's the partial derivative with respect to the first argument, the x argument, versus in this case the partial derivative with respect to the second argument, which is the y direction. So that will be the df dy partial derivative. So this is notation. So how do we in practice actually compute such a partial derivative? What does it mean to take a derivative in one direction, so in the x direction, while keeping the other direction, the y direction, constant? So that's what let's just look at what it means when we do a couple of examples in practice. So I'm going to do these examples in practice at low speed on paper. So let's do that. So we have a function again of two parameters, f of x and y, and it was given by x cubed times y plus x squared times y squared plus x plus y squared. So that means if you give me an x and a y, then I can plug them into this formula and it gives me one function value, a height if you wish. And now, of course, this function depends on x and y, and so there will be two partial derivatives. So there's two derivatives, two directions that we can walk in, which might have different slopes associated with them, depending on which direction we walk. So if you walk in the x direction, so if we change the x direction by a bit while keeping the y direction constant, what we're going to do in practice, we're going to use our normal differentiation rules on x, because we're taking the x derivative, and we treat y as a constant, because that's precisely what we want to do. We want to look at what happens if I change x, but I keep y constant. So I just pretend that y, wherever it occurs in this function, is just going to be some parameter, some constant parameter. It's not going to change. That's basically what I want to do. So let's see what that means. So in the first term here, x cubed times y, so y is just a constant, it might be just a number. So we know, for instance, if I would have to take the derivative of, say, for example, 3 times x cubed, we would know what to do, right? 3 is just a constant, so we just keep it there. So if I take the derivative of that, we would get, the 3 goes down here, so 3 times 3 times x cubed, right? Nothing surprising there. So here this constant, which is called 3 over here, is just called y over here, just one other constant. So I just treat it as a constant. I only have to look at the x cubed. That's the x dependent part. I'm going to take the derivative of that. That's going to be 3x squared. And I have to multiply it by this constant, just like I multiply here by this constant. 3x squared y. That would be the derivative of the first term. Similarly for the second term, it depends on x squared, so it depends on x actually, so as x squared, and it's multiplied by y squared. But again, if y is a constant, then y squared is a constant as well, because we're only interested here in the x behavior of this function. So I take the derivative with respect to the x behavior, but I'll just multiply by this constant y squared. If I then look at the third term, the x, well, it doesn't have any y, so that's easy. It's going to be 1. The final term just has y squared. So what's the derivative with respect to x of y squared? Well, again, y squared, we treat it as a constant. So the derivative of a constant is just 0, right? Plus 0. Or in other words, this partial derivative is going, with respect to x, is going to be 3x squared y plus 2x y squared plus 1. So that's the first partial derivative, the partial derivative with respect to the first argument, the x. And likewise, you can also take the second partial derivative with respect to the y. And not surprisingly, now we should treat this x thing as a parameter, as a constant. It's not changing, just the y which is changing. So we take the derivative with respect to the y, and we pretend that x is just like a number. So what does that mean? Just x cubed, well, that's just a number, times y. If I take the derivative, the y derivative of a number times y, it's just that number. So it's x cubed. That's the first part. X cubed is a number times y. If I take the derivative of that, I'll just get that number, x cubed. Same way for the second term. X squared is a number times y squared. Well, that I want to take the derivative of. That gives me 2y. So all in all, it will reduce to 2 times that number x squared times y. So 2 times y from the y squared. The x squared is just sitting here as a bystander, if you wish, as an onlooker. Third term, the plus x. My x is just a number. Looking at the y derivatives only, pretending x is just a number. The number doesn't change if I change y, x remains constant. So the derivative with respect to y of a constant is just going to be 0. And finally, y squared, I can take the derivative with respect to y as normal, so then just give me 2y. So that adds up to x cubed plus 2x squared y plus 2y. So that's the first example. So let's go to the second example. All these examples will be on the slides. So the second example is now this one. F of x and y is a function x cubed y plus xy times log of y. So again, I have two partial derivatives. The first one, df dx. If I take the partial derivative with respect to x, I'm going to treat all the y's as numbers again. So here the first term, it's x cubed times some number. This some number again being y. So, well, what's the derivative? The x derivative of x cubed, that's 3x squared. Now multiplied by that number y. Second term, x times y log y. Well, if y is a number, then y log y is also a number. So this is just a linear function of x, right? It's x times something. If something looks complicated, like y log y, this y log y, just some constant. So x times some constant, the derivative of that is just that constant, y log y. So this is the x derivative of function f. Now if I do the y derivative, I do something similar, but now I'm treating the x as the constant. So x cubed times y, well, x cubed is now, I'm taking the y derivative, so x cubed from that point of view is just going to be constant. Don't worry about it, just keep it as this, times the derivative of y, which is 1. So x cubed, it will be the y derivative of this first term. For the second term, the x is going to be a constant, so x is just to sit here, and I have to take the y derivative of this function of y, which is y log y. So we use the product rule actually, because it's it's a multiplication of two functions of y. The first part will give me, take the derivative with respect to the first y, it gives me just log of y. And if I take the derivative of the second one, it's going to be y times 1 over y, because remember the derivative of the log is 1 over y. Now if I work this out, I have this x cubed over here plus x log y for the first part plus x times y divided by y. That's just going to be plus x, provided of course we are in the domain of this function, which should not include y 0 or negative, of course, because otherwise in the first place this function would not have made sense. So this is the second example. Here I took again the derivative in these two different directions, implying that I take the other direction, which I'm not looking at the derivative of. It's just going to be treated as a constant. So let's go then to a third example. So it's given as a function z of x and y, and this function x squared minus 2 times y cubed to the power of 5. And again, I'm interested in the partial derivatives of z with respect to x and y, so z dx. Again, I want to treat y as a constant, just a number, and look at this as a function of x squared minus some number called 2y cubed, to the power of 5. Now what should I do? Well, here I have a composite function, right? So I need to use the chain rule. So as a function of x, the interior function is x squared minus 2y cubed, so x squared minus a number. So the derivative of that interior function is going to be 2x. And now I have to take the exterior function, which is raising something to the power 5. So I have to multiply this by the derivative of the exterior function, which is 5 times this interior part to the power 4. So 5 gets in front, gets reduced to 4. Or in other words, this comes down to 10x to x times 5 times x squared minus 2y cubed to the power 4. Similarly, the dz dy partial derivative. Now I'm going to treat x as being just some number and look at this as a function in terms of y only, x being a number. So again, using the chain rule, I'm going to take the derivative of this interior part, so x squared minus 2y cubed. If I take the y derivative of that, I'll just get the contribution from this second bit. This is going to be minus 3 times 2, or minus 6 times y squared, and then multiplied by the derivative of this exterior function, which is going to be again 5 times the number x squared minus this y dependent thing to the power 4. Or in other words, minus 6 times 5, that's minus 30 times y squared times x squared minus 2y cubed to the 4. Okay, so let's go back to the slides. So the first one was this one, so we just had this polynomial form with x's and y's involved, and I essentially took for each term the derivative. So in the case of the x derivative, I took the x derivative of the first term, treating y as a constant, gives me 3x squared y. Same thing for these other terms. So let me not go through this in detail again. It should be the same as we just did on paper. Same thing for the second example, where we had to use the product rule in particular to compute this y partial derivative. Actually, on the slide, I used a different notation here, where this first partial derivative was denoted with this 1 for the first argument. So this is the same as df dx, if you wish. And this f prime 2 then is the same as what I called df dy. And finally, we had this function, which was this composite function. I do something to x and y, and then I'll raise that to the power 5. So I had to use the chain rule, and I did this both with respect to x and with respect to y. So that's the first order partial derivatives. You can also look, just like with single variable function, we look at second order derivatives. You can also look at second order derivatives with partial derivatives, but now you can imagine that there's more combinations possible, because if the first derivative is with respect to x, then we still have a choice of whether we then again take a new derivative with respect to x, or perhaps we take a second derivative with respect to y, and vice versa. If the first derivative was already with respect to y, then we can again take one more derivative with respect to x, or we take the second derivative with respect to y as well. And basically the ways of notation, like this one for instance, you see here the d squared of z divided by dy squared essentially is the notation that we typically use here. Some other forms that you might sometimes see are here, which are sort of generalizations of the same sort of notation that I saw before, but I think these ones basically are by far the most common that we'll see. So just to be sure, so when I determine, or when I write d squared of the function z divided by dy dx, what I mean is I first take the partial derivative with respect to x, so the one which is rightmost here, and only after that I take the d dy, so the derivative with respect to y, of that result. So that's what this means. So let's do that. So let's take the higher order, or the second order derivative in this case, of one of these functions that we already actually looked at before. So let me do that again on paper. So I'm going to look again at this function f, which had so f of x and y is x cubed times y plus xy log y. So what we already just did was compute what are the first order derivatives with respect to x and with respect to y. So let me now compute the second order partial derivatives of that object. So those are 4 in total. So I can take the second order derivative in the x direction. So what does that mean? Well, essentially it means it's the ddx of df dx. So the x derivative of this x derivative. Well, the x derivative is already here, right? So I take the partial derivative with respect to x of this expression here. So I have 3x squared times y. I take the x derivative, so I presume that y is a constant. So what I get from the first term is the y, I just keep it there as a constant. And the derivative of 3x squared, that's going to be 6x. So 6xy. The second term, y log y, doesn't have any x's in it. So it's a constant from the point of view of somebody interested in x. The derivative of a constant, that's 0. So this is the whole answer for d squared f dx squared. Now let's look at the dy dx version. So I start with the first derivative with respect to x, but I take my second derivative now with respect to y. That's still possible because this first derivative is still a function of x and y. So I can take the y derivative of this object over here. So for the first term, it depends on y, just as a linear function, it's multiplied by 3x squared, but I'm now taking the second derivative with respect to y. So for that purpose, I treat this x squared, 3x squared as a constant. So that leaves me with 3x squared. Second part, the y derivative of y log y gives me two contributions. First one will be taking the derivative of the first y by the product rule, so plus log y. And the second one's taking the derivative of the log of y, so y times the derivative of log of y, 1 over y, this thing. So in other words, we get 3x squared plus the log of y plus 1, provided of course we are in the domain where log of y makes sense. So y is a number which is bigger than 0. Okay, so let's go to the next one. I would now like to compute df dx dy. So I first would take the df dy, the derivative of f with respect to y, this expression, and I'd like to take the x derivative of this particular function, which depends again on x and y, so I can do that. So I take the x derivative, the partial x derivative in the of this with this expression. So with the first term I get 3 times x squared. The second term x log y. So now I'm taking the x derivative, so log y is just a constant. So that leaves me with plus log y. And for the third term, it's just an x. So the x derivative of x is of course 1. So plus 1. And finally, d squared f dy squared. I take the first derivative with respect to y, and I take the second derivative with respect to y again of that number. So again, I take this expression, but now I take the y derivative of the first term, x cubed, is just a constant from point of view of somebody interested in y derivatives, so that gives me 0. Same way with the third term here, x, does not depend on y, so gives me a 0. Only this middle term here does depend on y, as log of y actually, multiplied by x, which I treat as a constant. So x times the derivative of log of y, that's 1 over y. Or in other words, x divided by y. Okay, so and that's the 4 different second order derivatives that we could take over here. And here you see these 4 expressions again on the slide. And you might have noticed actually that the order of the y and x derivative here and here where it's reversed, the way in which I compute this is different, but you see that the results are actually the same. That's a fairly general outcome for nicely differentiable functions. So this expression turns out to be the same. So finally, as an exercise at home, you can try actually for this particular function x minus y divided by x plus y, where of course you will need the quotient rule. So you will be able to actually compute the first derivatives with respect to x and with respect to y. You're also asked here to compute the second derivative, taking one more derivative of x of either of these things. And have a look at that example and see whether you can solve that as well. So that's how the mechanics go of computing partial derivatives. So the next thing will be how can we use those partial derivatives in order to optimize functions that depend on more than one, particularly on 2 different variables. So have a look at that in the next video.